In 1967, the Silver Bridge across the Ohio River collapsed in 40 seconds. 46 cars dropped into freezing water. 46 people died. Investigators found the cause. A single I-bar link, 1 inch wide, had cracked from the inside, and nobody had seen it coming because nobody could reach it to look. That disaster rewrote the rulebook for American bridges. Every structure built after it had to be inspectable, touchable, examinable by a human being with a flashlight and a hammer. So here's the question. You're an engineer, and you're designing a massive highway overpass. The deck is solid concrete. The girders underneath are steel, and they're hollow. Inside those hollow sections, the air is damp, the oxygen is rich, and corrosion is eating the steel alive from the inside. You can't see it. You can't reach it. And you know what happens when nobody can dot? What do? Most people, if they notice anything unusual about a bridge's underside, assume it's just the way concrete is poured. Formwork, construction residue, maybe drainage. The flat gray surface hanging below the road looks like structure, and structure, we assume, is solid. It isn't always. Sometimes what you're looking at is a door, a floor that isn't a floor, a false bottom engineered deliberately, hiding a world that most people will never know exists. By the end of this video, you'll understand exactly why that fake bottom is there, what it's protecting, and why a single design decision made in a handful of bridges may be quietly preventing catastrophes the rest of us never think about. The first explanation that engineers and curious pedestrians usually reach for is thermal expansion. Bridges move, not metaphorically, physically. A steel bridge in northern Minnesota contracts in January and expands in July by as much as a foot across its total length. Engineers account for this with expansion joints, the small gaps you feel your tires click over. If the underside of a bridge looks unusual, this thinking goes, it's probably related to managing that movement. The weird geometry, the extra layers, it must be about how the structure breathes. This is partially true. Thermal management is real engineering, and it does explain many design choices in bridge geometry. But it doesn't explain a sealed, hollow chamber. Thermal expansion needs clearance, not enclosure. If expansion were the only problem, you'd leave gaps. You wouldn't build boxes. The second explanation is drainage. Bridges sit in weather. Rain hits the deck, seeps through the expansion joints, drips down through the structure. Water pooling inside a bridge is a serious problem. It freezes, it corrodes, it adds unpredictable weight. So when people see a closed-off underside compartment, they often think, drainage reservoir, a space to capture water and route it away. Again, partially correct. Water management is critical in bridge engineering. But drainage systems are typically open channels with visible outlets. They don't need to be fully enclosed, structurally reinforced sealed chambers. You don't drain water into a box you can't easily access. The third explanation people land on is sound dampening or thermal insulation. The idea that bridges are increasingly engineered to reduce noise and temperature transfer to roads below. A sealed underside, this logic goes, is acoustic or thermal treatment. This does happen in urban bridges built over pedestrian areas, but it doesn't explain the access hatches. And it doesn't explain why, in certain bridges, the space behind the false bottom is large enough for a person to crawl through. All of them are incomplete, because the real reason for a hollow, enclosed, accessible chamber inside a bridge girder isn't about drainage or acoustics or thermal expansion. It's about what corrosion does to steel when nobody is watching, and what happens to a nation when it discovers, all at once, that its bridges have been rotting in secret for decades. Here's a number that should stop you cold. As of the most recent federal inventory, over 42,000 bridges in the United States are classified as structurally deficient. That means inspectors have found elements in poor condition, not necessarily dangerous, but deteriorating in ways that demand attention. And the vast majority of the damage isn't from traffic or weight. It's from something far more insidious. It's from moisture that got in and never got out. When sealed inside a concrete and metal structure and left to interact with trapped water and oxygen, corrodes at a rate that can surprise even experienced engineers. The process is electrochemical. Water acts as a conductor. Oxygen drives the oxidation, and the steel slowly converts itself into rust, which expands, which creates cracking pressure, which lets in more water, which accelerates the corrosion. It is a self-amplifying loop, and it happens in the dark inside the structural members nobody can see. This is the core problem the false bottom solves. But to understand why it solves it this way, you have to understand the specific anatomy of a box girder bridge. A box girder is exactly what the name suggests, a hollow box made of steel or concrete, running lengthwise under the bridge deck. These girders carry the primary load of the bridge, the weight of the road, the traffic, the dead load of the structure itself. They're chosen because the box shape is extraordinarily efficient at resisting both bending and twisting forces simultaneously. A single concrete box girder can span 80 meters without a support column. They are, in engineering terms, elegant. They are also, structurally, a sealed cavity. The inside of a steel box girder is an enclosed metal space. If moisture gets in through a welded seam, through a crack, through condensation on a cold night, it has nowhere to go. The interior surface begins to corrode. The problem compounds. And because the girder is structural, you can't just cut it open to look inside without compromising the very member you're trying to inspect. So what do engineers do? They build an access system into the bridge from the start. Maintenance walkway is constructed inside the box girder, essentially a narrow path, sometimes less than a meter wide, running the full length of the bridge interior. To enter this walkway, you need a way in. That way in is typically a hatch, set into the underside of the structure, concealed behind a flush panel that, from the outside, looks like the bottom of the bridge itself. That panel, that false bottom, is the access door to the bridge's internal inspection corridor, the Millau Viaduct in France, one of the tallest bridges in the world at 270 meters. Has interior inspection corridors running through its pylons and deck sections. Workers can enter the structure and physically walk through the bridge, while it carries 6 lanes of highway traffic overhead. The Hong Kong-Shumacao Bridge, crossing 55 kilometers of sea, has sealed interior systems with access chambers that maintenance crews navigate by golf cart. The Risund Bridge connecting Denmark and Sweden has compartmentalized interior sections, specifically designed so inspectors can examine the structure from the inside, even during winter storms. These are not unique. They are standard practice for any major box girder bridge built in the last 40 years. The false bottom is the visible face of an invisible maintenance system, but there's another layer to this, and it's the layer that most people miss entirely. The false bottom doesn't just provide access, it controls the atmosphere. Here's the critical insight. Corrosion requires 2 things, moisture and oxygen. Remove either one, and the reaction stalls. Engineers figured out that if you could seal the interior of a box girder and then alter the air composition inside it, you could essentially pause the corrosion process indefinitely. The technology to do this is called internal dehumidification, or nitrogen purging. In the dehumidification approach, a system of pipes and fans continuously circulates dry air through the interior of the girder, keeping relative humidity below 40%. At that level, the electrochemical corrosion reaction cannot sustain itself. The steel inside the girder, even if it has minor surface imperfections, effectively stops, corroding. In the nitrogen purging approach, oxygen is displaced entirely. The interior of the girder is flooded with nitrogen gas, inert, non-reactive, the same gas that makes up 78% of the air we breathe. Without oxygen, the rust reaction has no fuel. The steel sits in a nitrogen atmosphere, suspended in a kind of chemical stasis. Both of these systems require regular servicing. The dehumidifiers need filter replacement. The nitrogen levels need monitoring. The sensors that track interior conditions need calibration. All of that servicing requires physical access to the interior of the girder. The false bottom is the door to the life support system keeping the bridge alive from the inside. What changes when you understand this? More than you might expect. First, it reframes how we think about infrastructure failure. When a bridge makes the news, it's usually because something dramatic happened, a collapse, a closure, an emergency inspection. But the real story of bridge deterioration is almost always quieter and longer. It's a decade of trapped moisture, 5 years of missed inspections, a corrosion loop that started in a dark interior space and compounded slowly until the numbers in a structural assessment crossed a threshold nobody wanted to talk about. The bridges most at risk in America today are not the dramatic suspension bridges or the iconic cable-stayed structures. Those get attention, they get funding, they get tourists photographing them. The structures most at risk are the unglamorous ones, the 1960s-era highway overpasses, the municipal underpasses, the rural river crossings. Structures built before box girder interior management was standard practice. Structures whose interiors nobody ever thought to enter because nobody designed an entry point, the Federal Highway Administration estimates that repairing all structurally deficient bridges in the United States would cost approximately $125 billion. That number is the accumulated bill for decades of the false bottom problem existing in reverse. Not a sealed and controlled environment, but an unsealed and uncontrolled one, where moisture entered and nobody stopped it. Second, this technology is beginning to change how new bridges are designed, and the changes are significant. Modern long-span bridge projects now incorporate atmospheric control into the structural design from the earliest concept stage, not as an afterthought. The interior environment is engineered alongside the exterior form. The maintenance access routes are laid out with the same care as the traffic lanes above. Some bridge designs now include IoT sensor networks, humidity sensors, strain gauges, temperature monitors embedded inside the box girder and transmitting data continuously to a monitoring station. The bridge reports on its own internal condition, without anyone needing to enter it. This is the bridge equivalent of preventive medicine. Rather than inspecting periodically and hoping nothing went wrong between visits, the structure continuously narrates its own health to the engineers responsible for it. And here's the implication that should stick with you. The false bottom is only necessary because we reached an inflection point where the cost of not knowing what was happening inside a structure, then the cost of building a way to find out that inflection point was reached the hard way. Silver Bridge. Mianus River Bridge in Connecticut, 1983, a corroded pin failed. 2 people died. 129,000 vehicles per day suddenly had no crossing. The Fern Hollow Bridge in Pittsburgh collapsed in 2022. On the same morning, President Biden was scheduled to speak about infrastructure investment. The pattern repeats. Deterioration in the dark. Discovery too late. Consequences. The false bottom is the engineering world's answer to that pattern. It is an admission, built into concrete and steel, that what we cannot see will eventually surprise us, and that the only rational response to that truth is to design a way to see it. There's one more thing worth sitting with. The false bottom of a bridge is, in most cases, completely invisible unless you know what you're looking for. It blends into the understructure. It doesn't look like a door. It doesn't look like an access hatch or a maintenance entry or the gateway to a corridor that runs for hundreds of meters through the bones of a bridge. It looks like a section of the bridge's underside. That invisibility is by design. Not for aesthetic reasons. Engineers don't generally prioritize visual sleekness in access hatches, but because the panel needs to be flush, weatherproof, and sealed as part of the atmospheric control system. A panel that gaps or protrudes or looks different from the surrounding structure is a panel that might be compromising the environment. It's supposed to protect, but there's something worth noting about that invisibility. These systems work precisely because they're hidden. The maintenance walkways inside major bridges around the world carry workers through the interior of structures, while tens of thousands of cars pass above, completely unaware. The nitrogen purging system in a major cable bridge keeps the steel alive while commuters drive over it. Twice a day for 30 years without giving it a thought. The infrastructure that holds our world together is full of these hidden systems. The unseeable maintenance corridors, the atmospheric controls, the sensors measuring strain in steel you'll never touch. The engineering decisions made before a bridge is built that determine whether it will still be standing when your grandchildren cross it. Most of what keeps us safe, we never see. Most of what engineers design, we never know to be grateful for. And somewhere, under a highway you've probably crossed, there's a panel in the underside of a bridge that looks like nothing. Behind it, a walkway, maybe a dehumidifier, maybe a nitrogen line. Behind it, the reason the bridge is still there. The next time you're on an overpass, notice the underside. The geometry of it. The panels, the joints that shouldn't quite be there, you now know what you're looking at. If this kind of thinking, the hidden systems, the engineering that holds the world together in ways nobody tells you, is what you want more of, then this channel is where that lives. Subscribe, and we'll keep pulling back the curtain on the things that were always there, hiding in plain sight.